403 can be a fun lesson, and by fun I mean wordy and complicated sometimes. So I have 3 videos to go along with it. Hopefully it helps. Let's do the first example. Find the absolute maximum value for our piecewise function here. Now, when you're asked to find absolute min or max problems, you have to do 2 things. First of all is you find all possible minimum or maximum points. That's using a derivative test. First derivative test, which is where you set the derivative equal to 0, make your sign chart, and look for a sign change. Or use a second derivative test, which is where you find the critical points and plug them into the second derivative and check the concavity and see if it's a concave up or concave down, telling you if it's a min or max. I like that better a lot of times. It's usually faster. Okay, so that's the first thing you do is find the maximums just like you have been doing in section 402. But then you also have to find the actual minimum maximum value. This is a y-coordinate. And when you're given absolute max-min problems, you should be working on a closed interval. So in this case, we're starting at -3 and we're ending at 14. So that's our closed interval, and we're including -3 and 14. Okay, so we always have to check the actual min-max value and then our endpoints as well. So let's do an example. First of all, let's take the derivative of our function here. Derivative of 9 minus x squared is -2x. Set that equal to 0, and we get a critical point at x equals 0. And now I am going to do the second derivative test, which is where I take the second derivative here, and it's actually negative, always, constantly negative. So because the second derivative is always negative, it's forever concave down. I mean, if you think about what this graph looks like, it looks like this. So x equals 0 is a maximum of our function. So therefore, the point 0, 9, and the reason I'm plugging in a 0, I'm sticking it up here because that's where x equals 0 is defined in this domain. The point 0, 9, so I plug in a 0 for x, and that gives me my y-coordinate of 9. That's a possible absolute maximum point. Okay, so now the derivative of this part, I didn't do that yet. I don't really need to because the derivative of this is 2. So that's a constant. The derivative, and if you think about what this graph looks like, it's a line. So it's not going to have like any hills or valleys. It's not going to have a maximum like, bump like this. So I don't really have to take that derivative just because I know that it's linear and its derivative is constant. So I'm not going to get any critical points from that. Okay, so we have a possible absolute maximum at the point 0, 9. The critical point was at 0. You have to always find the actual point. This is the y-coordinate. So our answer could very well be 9 for this problem. Honestly though, best thing to do is graph this. It's just so much easier sometimes. So from -3 to 4, that's this parabola here. 9 minus x squared looks like this. It touches the y-axis at 9. This is at +3, and then you can just keep going, plug in a 4 to figure out where this point is, and then that tells you that the point there is -7. And then plot this point, or plot this graph. You could, really just plug in points, like start with 4, make sure that they touch. So when you plug in a 4 here, you get 8 minus 15, which is -7. And then honestly, you really just need one more point. So plug in the endpoint, stick a 14 in there, and then subtract the 15, and you end up with +13. So that's your line right there. That's from 4 to 14. So if you look at the picture, my absolute maximum is not 9. Remember to check the endpoints. The endpoints are possibilities. So in this case, the absolute maximum is actually 13. So you start out by finding all the possible minimums and maximums, like the relative, which is the roller coaster ones. In this case, because we were looking for maximums, I didn't really need to know about minimums. But then you also check the endpoints. And the final answer is always the y-coordinate. Okay, same problem, same equation, just finding the absolute minimum. So this graph does not have any relative minimums because relative, remember, is roller coaster. This is a relative maximum because it's like, curvy. So, but it doesn't have any relative minimums. There is an absolute minimum down here though. So the absolute minimum would be -7. And that's just because that's the lowest point in our closed interval, the lowest y coordinate. The final answer is the y coordinate. And that's when you're asked for absolute situations. Okay, let's do one of these optimization problems. A 7-foot strip of metal, 4 feet wide, is to be made into a small open trough, I think that's how you say that, by bending up 2 sides on the long side at right angles to its base. The sides will be the same height. If the trough is to have a maximum volume, how many inches should be turned up on each side? Okay, let's deal with this. First of all, that's what a trough looks like. And we don't have these pieces. We have this situation. We have like a piece of metal, 7 feet this way, 4 feet this way, and we're going to fold 2 sides up. We don't know the distance yet, but we know that this section and this section are going to come up like 3D towards you and make a right angle right there. So let's just talk about the steps of setting up these kinds of problems. You start by reading it real carefully. It's always important. Read it a few times. And you identify the quantity that needs to be optimized. That's going to be the objective function that you're going to differentiate, meaning we need a maximum volume in this case. So in this problem, the volume function will be what we need to find the derivative of because we need to find the maximum of that function. And then the constraints, this is the fixed quantity that's true regardless of the solution. And then we use the constraint to rewrite the objective function in one variable. So a lot of times you're given a lot of information and you end up with more than one variable, and you don't want to differentiate an equation with more than one variable because then you end up having to use product rule with 2 variables and it gets really ugly. You can't really do it. So you want to use what you're given. You usually have a substitution situation where you need to use another equation to plug it into the equation you're going to use the derivative on, just so you can make it one variable. And then we need to talk about the domain of the objective function because sometimes some of the x values don't fit. So then we just go through the process at that point of what you've been doing, find the critical values, and then use one of the derivative tests to find the maximum or minimum. And then go back to the equation or to the question and make sure you're answering what they're asking. Don't just stop and move on. Okay, let's try all this. So there's our steps. Our objective function is the volume of our trough, 3D. So it's going to be length times width times height. Notice that is 3 different variables. We don't want that because you'd have to take use the product rule with 3 variables on here, and that's messy, messy stuff. Okay, so the constraints, what's true no matter what? Well, the length is 7, not changing. The width is 4 for the flat piece of metal, but we're going to fold it up. So the width is actually just this little section here. So it's really 4 minus 2 x's because the x's is the height. X's are the height. So our situation now can be written like this. And our objective function is now in one variable. Okay, let's talk domain about this now, because we have to think about feasible situations for x. Like x is the height of a trough here, so it can't be negative. And the lowest it could be is 0, because if x was 0, then there is no height, so it's still flat. So we can start it at 0, but then let's look at this situation. This is where we can decide how high it can get. Because what if the width was 0? Think about what's happening is we're taking this section here and we don't know how big this area is. I mean, what if we folded it all the way here? So both of these ended up right here. And now there is no width. What if the width was 0? Well, that would be basically the highest that x could go. If we set that equal to 0, you end up with x equals 2. So that's our domain, is from 0 to 2. We can't have any negative numbers. The lowest the height could be is 0, which means that we still have a flat piece of metal. And the highest it could be is if the width was 0. So you just kind of think about it in that case and go from there, because now we have our function. I simplified this. This is our volume equation. I just distributed because now we can take the derivative, set it equal to 0, solve for x, and get our possible maximum value. This is our critical point. So let's use a sign chart like we've been doing. Plug numbers in. Plug a number in between 0 and 1. It's a positive number. I'm plugging it into the derivative equation. Oh, this one here. And then plugging a number in between 1 and 2. We get a negative. So check it out. We have, this is the first derivative test. Because the sign of the derivative changes from positive to negative at a critical value, that means that x equals 1 is a maximum. Because if we're talking about the graph of v, it has a positive tangent line and a negative tangent line, and this point right here is where it's flat. So that creates a maximum. Personally, I like the second derivative test. So the second derivative, I mean, this is enough, just so you know, this is enough to prove that we have a maximum. This is considered the first derivative test. The second derivative test, however, that's where you find the critical point. So I didn't do any of this. Pretend this never happened. I found the derivative. I found the critical point. And then what you would do next is find the second derivative. So if this is the first derivative, the second derivative is just negative 28. And the next thing you do is plug in the critical point into this equation, because that tells you the concavity. The second derivative tells you concavity. So if you know that you have a critical point, which is a horizontal tangent line, which means it's going to be a minimum or a maximum most likely, then if it's concave down, which it is in this case, it looks like that. Well, there's nowhere to plug it in. There's no x to plug in. The second derivative is forever concave down. So the critical point absolutely represents a maximum. So now let's make sure we answer the question, which is the strip of metal will need to be turned up 1 foot on each side to create the maximum volume. And that's because when x equals 1, it created the maximum. Okay, hopefully that makes some sense. Let's move on to the next video.